So starting this fourth week, I want to first go over a quiz I gave, this second quiz for the class, and that's what we'll go over on this first lecture. Okay, so just to remind you, here was all of our equations so far for relativity. And so now, going over this quiz number 2, it said, the question was, in our Frank-Marey system, an event occurred at x prime, so x prime was 60 meters, so this is x in Mary's frame. T prime was 8 times 10 to the minus 8 seconds. So this was some event occurred at this x and this t. I could have plotted it out on the Minkowski diagram. And Mary's frame is moving at a velocity of 3/5 c. And we just wanted to know, what is the x position in Frank's frame of this? So again, if we were looking at our plot here of x and ct and our Mary's plot, which is x prime, and this is our ct prime. We're just looking at some point out here. There's some point right there, x prime, ct prime, and we just ask, what is the x value at that point in Frank's frame? And so we just come back over here, use these formulas right here, and we can say x is equal to x prime plus vt prime all over the square root of 1 minus v squared over c squared. X prime is 60 meters plus 3/5 c times t prime, which is this, 8 times 10 to the minus 8 seconds, divided by the square root of 1 minus v is this, so if I squared, that's 9/25 c squared. So the c squares drop out, and this is just 1 minus 9/25. Okay, so this becomes, well, the denominator just becomes 1 minus 9/25 is 16/25. Take the square root of it, and that's 4/5. So the denominator is just 4/5. And the numerator is 60, I'll leave out the units here, plus 3/5 times the speed of light. I better put in 3 times 10 to the 8th, and then times 8 times 10 to the minus 8. 8 times 10 to the minus 8. Okay, the 10 to the 8 and 10 to the minus 8 are gone. This is 9 times 8 is 72 over 5. So we end up with 60 plus 72 over 5 divided by 4/5. I think I'll make this 5 over 5. So this is 5 divided by 5. So that's 300 over 5 plus 72 over 5 divided by 4 over 5. Well, all the 5s are gone. So it's 372 over 4. And that ended up being 93 meters. Okay, so you just plugged it into this formula. The second question of this, I think there were 6 questions, they wanted to get, what is the time? What is the t? So now, if we were to write this point right here in Frank's frame, this would be 93, right there. Remember, in Mary's frame, it was 60, right here. But then again, remember, Mary's frame is just the distance. There's Mary's distance, that's 60, but what's way over here, there it is, what it is in Frank's, that's the 93. Okay, so now let's get the time, t. is equal to t prime plus xv over c squared, x prime v over c squared, divided by the square root of 1 minus v squared over c squared. Okay, so t prime, 8 times 10 to the minus 8, plus x prime, which is plus 60, times v, which is 3/5, c, which is 3 times 10 to the 8th meters per second. That's divided by c. Actually, what I'm going to do, instead of writing the c, why don't I just make it c for a minute? That's just c divided by c squared. We'll make it c squared for now, right there. Divided by the denominator. The denominator is the same as I had before, so it's 4/5. So this is 4/5. Okay, so now we have 8 times 10 to the minus 8. This right here, one of the c's are gone, and so we get 180 over 5. Well, this is 12 times 3, that's 36, plus 36, and then divided by c, which is 3 times 10 to the 8th, right there, divided by 4/5. Well, the 36 over 3 is 12. Bring that up to the top. This is 12 times 10 to the minus 8. So if I add those two together, this just becomes 20 times 10 to the minus 8. 20 times 10 to the minus 8 divided by 4/5. I can put the 4 there and bring the 5 up above. 20 over 4 is 5, times 5 is 25. So this is 25 times 10 to the minus 8. And this would be in seconds. Okay, so again, just plugging in to find, so that's what this point would be in time. This would be 25 times 10 to the minus 8 seconds. That's what this value, and this would be 93. 25 times 10 to the minus 8. Whereas, remember, in Mary's frame, this right here, the distance over this way is x, which would have been the 60, and the distance up this way would have been the time, which would have been 8 times 10 to the minus 8 seconds. Okay, so all we did was go from one to another right there. Okay, now the next problem was, there wasn't anything to calculate. You have a spear. Let's just say that's your spear. And you have a pipe. You have some pipe right here. And I think they said when they have the same length when they were both at rest relative to each other. Now you throw the spear through the pipe. And you ask, when the spear is exactly in the middle of it, which of the following happens? Now, one of them is the spear shrinks, so it looks like this. It's just shortened in there. The other one is that the pipe shrinks and the spear sticks out from both ends. Another one is that they both shrink and it just barely fits. And the fourth one is any of these can happen, depends on the speed of the observer. Well, the correct answer was all of the answers are possible depending on the speed of the observer. You'll notice right here, if you're standing on the pipe and the sphere goes by, it will shrink. Your pipe won't shrink, but you will shrink right there. The sphere will shrink. What happens if you're standing on the sphere? Well, then the pipe is going the other way. You're not moving. The pipe's going this way, and it shrinks. This one down here. Suppose you're going at half the speed of the sphere was going relative to the pipe. So what it looks like is the pipe's going this way and the sphere is going that way. So it's kind of like, suppose this sphere was going this way at 100 and this wasn't moving. And you'd say, oh, the sphere shrinks. But what happens if you were going this way at 50? If you were going this way at 50, you'd see the sphere moving this way at 50, and you'd see the pipe moving the other way at 50. You'd see them both shrink equally, and again, it would just fit inside. So any of these are possible depending on the speed of the observer. Okay. The fourth one is, we have a spaceship moving away from an observer. So he got some spaceship moving at point 8C. And he fires a missile in the forward direction at point 5C. And we want to know, what is the person here see the speed of the missile at? Okay, so again, this is just my Mary. My Mary is moving. This is Mary in here. And her velocity relative to Frank, there's Frank. The velocity is 0.8c. She throws something in the x direction, which is her ux prime, would be 0.5c. And we want to know, what is Frank see? Ux equal. That's what we want. Okay, so plugging it in, we get ux is equal to, again, there's our formula right here. This is everything. Ux prime plus v all over 1 plus ux prime v all over c squared. Add these up, that's 1.3 c all over 1 plus the product of these, that's 0.4 c squared over c squared. So that's 1.3 over 1.4c, which is 0.93c. Okay. And then question 5. 2 events occur at the same time in Mary's frame. So again, if we were to draw it, again, our picture Minkowski diagram, there it is, and 2 events occur at the same time in Mary's frame. Remember, same time is this. So we have an event here, and we have an event there. So we could call that event 1 and event 2. So you got an x1 prime, ct1 prime, and you have an x2 prime, ct2 prime. That's what they would look like. And on Frank's frame, down this way and this way, we would have an x1 ct1. Over here, we would have an x2 ct2. Okay, and so we said, and 2 events occur at the same time in Mary's frame. That means that this time and that time were the same. T2 prime minus T1 prime was equal to 0. They were the same time. And they're separated by 1 meter. So this separation in Mary's frame going up this way is 1 meter. So x2 prime minus x1 prime is equal to 1 meter. So that would have been this distance right there. Now they say, what is the time difference between these 2 events in Frank's frame? So we're going to want to find T2 minus T1 in Frank's frame if he measures the spatial separation as 2 meters. So So remember, Frank would be the distance from here to there. It'd be this distance right there. So x2 minus x1, they said, was 2 meters. Okay. Well, you noticed if I just say, let me just come back here. We need to get the velocity right here. We could probably guess what it is, but I won't guess. x2 minus x1 is equal to, and now we'll go ahead and we'll plug in our x. We'll plug in this equation right there for our x's. So that's x2 prime plus vt2 prime all over the square root of 1 minus v squared over c squared minus x1 prime plus vt1 prime all over the square root of 1 minus v squared over c squared. Okay, well, we said that the two times were the same, so this term and that term cancel out. And x2 minus x1 was 2 meters. x2 prime minus x1 prime is 1 meter, divided by the square root of 1 minus v squared over c squared. Remember, this is just my gamma is just 2 right here. We already know what that is. Remember, I could square both sides and flip everything, but we already knew it's 86% the speed of light. So v, which was the square root of 3 over 2c, which is 0.86c. Again, that's when gamma gave me the factor of 2. We could have probably seen that here because we see the factor of 2 in the length right there. Okay, but we wanted to get T2 minus T1. So now we can say T2 minus T1. Again, we're just plugging in our formula over there. This is T2 plus x2 prime v all over c squared divided by the square root of 1 minus v squared over c squared minus T1, that's prime right there, minus T1 prime plus x1 prime v all over c squared divided by the square root of 1 minus v squared over c squared. Okay, we can pull out, they have a common denominator, and we know what that 1 over the square root of that is just 2 right here. So that whole denominator just brings me a 2 in the numerator. And then we've got x2 prime minus, T2 prime minus T1 prime. T2 prime minus T1 prime is 0, so those two canceled out. Now we get x2 prime minus x1 prime, which is 1 meter, 1, times v over c squared. V all over c squared. And we know what v is. V is right here. So this is 2 times the square root of 3 over 2. C over c squared just gives me a c in the denominator. The 2's drop out. And so it's just 3 over the square root of 3 over c, which is the square root of 3 all over c, which is 3 times 10 to the minus 8, 3 times 10 to the plus 8 meters per second. Bringing that up to the top, it's 10 to the minus 8, and that's this over this is 0.57, so you end up with 0.57 times 10 to the minus 8. I have the answer in nanoseconds, which is 10 to the minus 9 seconds, so I need to make this 5.7 times 10 to the minus 9 seconds, so that's 5.7 nanoseconds. And so there was the answer to that one. And then the last one here, number 6, a particle has a half-life of 6 seconds So when we say it has a half-life, we're talking about the proper time. So the proper time is equal to 6 seconds. What is its half-life if it moves at 0.8 c? Well, that means his clock is running a little bit slower. And so we know that t is just t naught square root 1 minus v squared over c squared. Okay, and we could have done it here and drawn 2 points. We would need 2 points right there. But we got it here already. So this is just 6 all over the square root of 1 minus 0.8 c. V was equal to 0.8 c. So that's 0.64 c squared over c squared. That's 0.64. 1 minus 0.64 is 0.36. The square root of 0.36 is 0.6. 6 over 0.6 is 10. So he lives longer. He's moving faster. His clock's, when we look at him, he's living longer. He's going to live for 10 seconds. Okay, so there was the quiz. One other question I wanted to go over here was on one of the homework ones. This is where we had a pole that was 10 meters long going into a barn. I don't quite, here's my barn right there. We'll just have both doors open, the front and the back right there for a minute. So here's the back of the barn. Now the depth of the barn is only 5 meters. So if I didn't draw this to scale, I should make this one like twice that long. So here it is. Here's 10 meters. Now, we're standing here. I guess this is relative to Frank. Frank is standing here by the barn. And this person carrying this pole or rod is going to move at 86% the speed of light. 86% the speed of light. We know when you go that fast, that gamma factor that we had before is 2. We already did that right here. So this pole shrinks. Remember, lengths contract. It will only appear to Frank to be 5 meters long. So that would mean that when this end of the pole is near the back of the barn, this end should be near the front of the barn. And if this were, let's say, a clear barn, glass barn, and we could take a picture of it and we could see the pole exactly within the barn. But now, if we look at it from the point of view of the person running with the pole is 10 meters. He doesn't see his own pole shrink up. And we have the barn, but the barn is moving towards him. He sees the barn much shorter. He sees it shrunk half as much. So he sees the barn is only 2.5 meters deep. And he's going to say, there's no way I'm going to fit inside that barn. And so what's happening here? Does it fit inside the barn? Well, Frank's going to say, yes, I got a picture of it right there. But what does Mary say? Mary says, no, I never saw it inside the barn. If we draw a picture of our XCT, there's Frank's picture, and Frank has the barn here. So here's let's just call this part right here is the left part of the barn, left barn. This is the right part of the barn, the right edge. And so what are they doing? Their line just goes straight up. They're not going anywhere. So there's the right, there's the left. Now we have Mary's coordinate system. So Mary's out like this. like that. So there is the x prime ct prime. So this, since Mary's going to be right here. Mary's holding on to the left end of the pole right there. So this, since this is Mary, this is also the left end of the pole. So here's the left pole right there. Now we know what this point is right here in Frank's frame. This point right there is x equal 5, because the barn is 5 in Frank, so that's 5 times 0 right there. If we wanted to get the red point for this spot, what is this on Mary's frame? Well, we could just plug in our coordinate system transformation, and we could say x prime right here. X prime is equal to x, which is 5, minus vt, sorry, x, let me write the equation out here first. X prime is equal to x minus vt all over the square root of 1 minus v squared over c squared. Well, t is 0 there, we just saw. T is 0. X is 5. 1 over that, that's 2. Remember, we already said that was a fact. 1 over square root is 2. So this becomes 10. So on Mary's frame, this x value is 10. The t is not 0. T is 0 everywhere along here. So, and t is growing this way. So down here, t is going to be some negative value right there. So if we wanted to find the t value right there, we could say t prime is equal to t, which is 0, minus x, which is 5, v, which is the square root of 3 over 2, c, all over c squared, which just gives me a c in the bottom, divided by the square root of 1 minus v squared over c squared, which just gives me a 2, another factor of 2 in there. The 2's drop out, and you get t prime is equal to minus 5 square root 3 all over c, or if you wanted to plot out ct, remember this is really ct, you could get rid of the c. So this point would really be minus, sorry, I should do it in red, minus 5 square root of 3, minus 5 square root of 3. It's a negative number. We said it should be negative. You're coming down this way, right here. Well, now, this, so you noticed when the left end of the, so now we need to show the path, well, this was the left end of the pole coming down right there. The right end of the pole, I know, is eventually going to hit right there, because that's it. So here's the right end of the pole coming down like this. So this is the left pole end of the pole. This is the right side of the pole. Well, we can see when the left side of the pole is equal to the left end of the barn right there. So at this point right there, that's when the person holding the pole right there is right at the left end of the barn. So we could draw, let me just draw the barn right there. So here's the barn. So they're both right there, the left end of the barn and Mary right there. But at this point, where is the right side of the pole? Well, this is the right pole right there, and the right side of the pole, where is it at the same time as this time? Well, remember, this is all equal times, so the right side of the pole is right there when the left end was here. And you can see on Frank's frame, that's past the end of the barn. It's past the end of the barn right there. And likewise, when the right side of the pole is at the right end of the barn, so I'm just going to draw again, we'll put the barn right here. And now, here's the right end of the pole equals the right end of the barn. That's right here. The right side of the pole, the right side of the barn is right there. Where is that? Where is the other end of the pole? Well, it's not this way. Remember, these are equal times, so it's down over here someplace. So it's right there, and it's past the end, just like it is over here. So everywhere along this point right here, x prime better be 10. Why? Because this is the right side of the pole. On Mary's frame, Mary's always at the origin. This is always at x prime equals 0. That's the other end of the pole. This end of the pole to Mary is always 10. So this is x equal 10 right here. Just like in Frank's frame, this is always 0 and that's always 5 right there. So Mary is going to say, no, I was never inside. This occurred first because this is some negative time, and this is at 0 time, because this is how we defined our 0 time when Mary got to the left end of the barn right there. Now, I could have instead, this is all written out in terms of Frank's diagram right here, but let's just say we look at it from Mary's point of view. From Mary's point of view, I should put her straight up and down. So Mary, there's Mary, x prime, ct prime. Frank is moving to the left, so his doesn't move in, it moves out when you go to the left. So Frank's x ct would look like this right here. And now we have the pole in Mary's frame. The pole is between here and here, and that doesn't move in Mary's frame. So this is the left end of the pole. This is the right end of the pole. So this is right pole, left pole. It's like that right here. Okay, now what about the barn? Well, the barn, this right here is the left end of the barn, because so the barn's going down like this, and the right end of the barn is going, his barn is pretty short right here, so it's going down like that. So there's the right side of the barn, there's the left side of the barn, and you'll notice right here is when the right side of the barn hit the right side of the pole. That is right here, right side of the barn equals right side of the pole. So here's your barn right here. Again, it's at some negative time in Mary's frame. And then later, when this end gets over to here, that's when you're in this case right there. And it looks like this. And this is at t equals 0. And this was our t equals negative, whatever that was, 5 square root of 3 over c, minus 5 square root of 3. That's what ct is right there. So you can look at it from either point of view. It's just that Mary never sees the pole completely in the barn right here. Now, we could have tried to fool it a little bit. I just wanted to suppose, instead of going through a barn, suppose here's the pole going, and instead of going into a barn, you have a ring, and you're just going to drop the ring over the top of it. So let's just say the ring is 5 meters. Instead of a barn, we have a ring that's 5 meters in diameter. And if this 10-meter pole is going at 86% the speed of light, then this point right here is going to shrink down to 5 meters. And so Frank says, we could just drop this thing over the top right there. Just drop it over the top. And now Mary can't say it didn't drop over the top. But what would Mary say? Mary would say, you cheated right here. She'd say, you know, this event occurred over here. It's not the same as the event over here. And when you drop it, that means that these two aren't at the same height. They're not just going to be level. It's going to kind of bend a little bit right here. And so then you can just go right on through, right there as it bends down. So things can appear a little bit warped because because of this time it takes for light to get to you. Okay, so hopefully this answers some of your questions you might have had, at least on the homework or on the quiz. Okay.